Alrighty, folks. Hello and welcome back. This is, I believe we are on lecture number 4 right now. Maybe it's lecture number 5. I can't remember off the top of my head. But what we're doing today is we are going to finish up Module 1, and then we're going to jump right away to Module 2. So again, in Module 1, our key aspects here is designs of experiments. So we've already looked at a one-way ANOVA. We've modified a one-way ANOVA to include a blocking factor. So the blocking factor, again, is when we have those experimental units that are not homogeneous in the sense that one of or multiple of the experimental units has an inherent bias. So if we look at the gasoline example, so we were trying different brands of gasoline. We have brand A, B, and C. If one or more of the cars worked well independently, so always had better mileage independent of what brand of gasoline they would use, that would add an inherent bias to the experiment in itself. So blocking was a way of being able to not control that, but kind of control that, but a way of being able to monitor if this is in fact happening. But still, at the end of the day, what we were still primarily testing was the primary factor, was that different brand of gasoline, which one is the providing the best mileage overall. So what we're going to be finishing up today is the two-way ANOVA, so when we have two factors. So where the slight variation of this is going to come into play, we have a primary effect, so the effect that happens from the first factor, the effect that happens from the second factor, but there is a secondary effect that there's a potential interaction between the two factors. So they behave differently at different levels. So we'll need to look into that as well. And that's going to round out all of the experimental design that we're going to be talking about. Again, this is continued on in another class, that's Stat 3504 if you're looking to do a stat minor. And after that, module number 2, we're going to be focusing on model building. So that's really going to pick up on what we were doing back in Stat 2601. All right, so let's jump into the two-way ANOVA. All right, so for a two-way ANOVA, many response variables are affected by more than one factor. Because of this, we must often conduct experiments in which we study the effects of several factors on the response. So again, this could be extended up to multiple factors, so n different factors. As long as we understand what's happening with two factors, then we'll be able to build upon that. So that's where our focus is going to be on the two factor here. So here we study the effects of two factors on a response variable. So we again make use of the completely randomized design, so the CRD for short, for experiments that involve two crossed treatments. Now by crossed treatments, what do I mean by this? So we have two different factors. I have my first factor, I have my second factor. Each factor has different levels. So we're looking at all possible combinations of these. So the example that we gave back in the first or second lecture was when we were talking about the performance of students in a stats class based upon what term the class was held. So we had fall, winter, summer, and how it was delivered. So it could be in person or it could be online. So crossed would mean all possible combinations. So we have three possible options for the first. So that's fall, winter, summer. We have two possible options for the second, which is online or in person. So a total of 6 possibilities overall. Each one of those possibilities are valid. If there was something in there that there was a forbidden configuration, something that couldn't happen, it wouldn't be a cross treatment. So what, again, we're talking about is all possible combinations are in fact valid. So we label the treatments we label the treatment factors as factor 1 and factor 2, where factor 1 has A levels coded as 1 all the way up through A, and factor 2 has B levels coded 1 all the way up through B. And we will assign M randomly selected experimental units to each one of the treatments. So in this case, if there is A possible outcomes for the first factor, B possible outcomes for the second factor, all possible combinations are valid. The number of treatments we would have is A times B, and we would assign M experimental units to each of these A times B treatments. As I've already said this part, the factors are crossed if every combination of levels may be observed. So there's no hidden configurations that can't possibly happen. And as I said already, there's a total of A times B treatments. All right, so a couple assumptions. All of these play exactly the same as to what we've been doing up to this point in time. So in order for a 2A ANOVA to produce valid results, the following assumptions must be met. Of course, we have the mutual independence. So we've had independence this entire way. There is no difference here. So the two variables for testing should be independent of each other. The samples of the experimental units associated with the treatments are randomly selected independent samples. That is, we have employed a completely randomized design, again, CRD for short. So if we look at the two factors, they should be independent of themselves, and how we assign those experimental units should be, in fact, done randomly. All right, so for each one of the possible treatments, so we have A times B different populations. These populations must all follow a normal distribution. So for each treatment, again, there's A times B treatments. For each treatment, the possible values that could come from that must come from a normal distribution. And of course, last but not least, we have that constant variance. So same as before, we can test in exactly the same way, no difference here. So this is, again, we assume that the variance is constant over all of the different treatments. We don't know this for sure. We could run our experiment. We could get for each one of the treatments a standard deviation, and if 2 times the smallest is greater than the largest, then that is enough for us to say constant variance overall. All right, so a little bit of notation here. So I have 2 indices to start with. We have I and J. I is indexed starting at 1 all the way up through A, so this is going to represent the factor 1, and J is indexed starting at 1 all the way up to B, so this is going to represent factor 2. So the outcome of the experiment, we have X sub ij, comma K. So the ij is, again, referring to the specific treatment we're dealing with. So when I is coming from factor 1, J is coming from factor 2, and K is going to represent what experimental unit we are in fact dealing with. So if for each treatment there is 3 experimental units, there's going to be an IJ1, IJ2, and IJ3. All right, so we have for each one of the treatments, there is going to be a mean for that treatment. So that's the X sub ij bar. For each one of the, not treatments, but for each one of the levels for factor 1, there is going to be an average. So that is X bar sub I dot. So when I represents my factor 1, and I don't care what the second factor is. So we're looking, if it was level 2 of factor 1, I don't care what factor 2 is doing. I think I said that correctly. I don't care what factor 2 is doing. I'm looking for all of the level 2s of factor 1. And the same idea is when I don't care about factor 1 and I care about just factor 2, that's my X bar sub dot J. And of course, for the entire experiment, we have an average of that. That's just X bar. So now we need to break up that total variation. So here I have 3 summations. Again, I don't really want you to focus too much on the 3 summations that's happening here. To count the total sum of squares, all we are simply doing is we've run the experiment. For each treatment, we have the M possible, or the M outcomes from that. So we look at each one of the outcomes for the entire experiment. So I grab one of the outcomes, I subtract it from the center of the experiment. So that's what we have here, the X sub ij comma K, subtracted from the center of the experiment. Now I don't care if it's to the left or to the right, so if it's smaller or greater than, I just want to know how far is it away from the center, so I'm going to square that, and I'm going to do that for each one of the possible outcomes. So there's A times B treatments, but there's M experimental units for each one of the treatments, so we have A times B times M. That's going to be the number of X sub ijk's. And again, each one of those we're going to subtract from the center, square it, add them all up. That's going to get me my total sum of squares. So that would be the total variation for the experiment in itself. From here, we want to break it up into things that we can, in fact, explain. So there is going to be a factor 1 sum of squares. There's going to be a factor 2 sum of squares. Now, there's also going to be an interaction. So if we think back to the blocking example, we had the total variation. We broke it up from what do we get from the first factor, well, the only factor, what do we get from the blocking, and then there's going to be that error in between. So here we get, what do we get from factor 1, what do we get from factor 2, so this is the primary outcomes that we get, and then there's going to be that interaction. So what is the interaction between those two factors? And then last but not least, we are going to have the what we can't explain, that's going to be our error sum of squares. So the question is, well, how do we calculate all of these? I'm going to show you the formula, but again, I'm not going to ask you to memorize the formula. R is going to build our ANOVA table for us, but I want to at least give you where this is all coming from. And it's just taking this total, and we're going to decompose this into the 3 parts. The 4th part is going to be the error. We're not going to have a nice formula for that. Well, we're going to be able to rearrange the total, subtract the 3 that we know, and what we're going to be left with is the error. All right, so the sum of squares for factor 1, I have a scalar here. This is my b times my m. Basically, I'm just breaking down those 3 summations into just a single summation that focuses on that first factor. So I'm indexing starting at I is equal to 1 all the way up to a, so the total number of levels for my first factor. And I'm saying, well, what is the average for each one of those levels? Not treatments, but each one of the levels for the first factor minus the center of the experiment squared. Same idea for the second. Again, I'm breaking down those 3 summations into a single summation. So I have a scalar in front. This is a times m. And now I have a sum starting at j is equal to 1 all the way up to b. So I'm going to go through all the levels for factor 2. And I'm saying, what is the average for each one of the levels of factor 2? Subtract that from the center, square them, add them all up. That's going to get me my factor 2 sum of squares, or SS2. So I have SS1, SS2. Last but not least, the interaction. Now, calculating these ones, this isn't too bad. The interaction, I don't want to do this by hand. Thankfully, we won't have to. So in terms of the interaction, how do we calculate this? Again, we are breaking down 3 summations into just 2 summations. So we are indexing starting at I is equal to 1 up to a. So we're going through all the levels for the first factor. We're doing j is equal to 1 all the way up to b. So all the levels of the second factor. We're scaling it by the m experimental units that we have here. And what am I doing? I'm taking, well, what is the average of the treatment? So again, x sub ij is going to represent the specific treatment. We're taking the average, that's the x bar part of it. I'm going to subtract what is the average for level I of factor 1. What is the average for level j of factor 2? So I've kind of removed a little bit from my first, removed a little bit from my second, and what I'm going to do, I'm going to add in the center of the experiment again. And then I'm going to square all of these. So this is definitely something I do not want to calculate by hand. Simple as that. This would be a pain. We could do it, but you'll see even for a small example that we're going to be playing around with here, there's a large amount of calculations, and one small mistake will throw us right off. So I have gotten questions about, well, what are we going to expect to see when it comes to the midterm and the final exam? Great questions. Again, I'm still not going to ask you to do these calculations by hand because this would take you the entire exam period, and we're not looking to do that. So think of the assignments. In the assignments, there is a heavy R component. So you have to do the programming there. You get the output, then you interpret the output. So what we're going to do when it comes to the midterm and when it comes to the final exam, I'm going to just give you the output. So I'm going to do all the work inside of R. I give you the output. So it's kind of like you skip that step that you would have done in the assignments, and potentially this is where some people make those little mistakes in terms of the coding. I'm going to give you the output. It's just your job to interpret what's happening with that output. So I'm not going to ask you again to do these calculations. I'm going to give you the ANOVA table, and then I'm going to ask you to run a hypothesis test based upon that ANOVA table, something along those lines. But it's not going to be a coding. You're going to get the output. You just need to interpret the output. So we have SS1, we have SS2, we have SSint. So I can calculate the variation from factor 1, the variation from factor 2, the variation from the interaction. This is how I then can calculate the error. That ran into the example. That's the next slide over. So let's jump to the next slide over. So this is my total, my sum of squares total broken down into the 4 components. Again, we have a formula for the first, second, and third, just not for the last one, but I can rearrange all of this So I can solve what SSE has to be by calculating what the total is minus the variation from the first factor, minus the variation from the second factor, and minus the variation from the interaction. All right, let's go back for a second there. Let's look at the example that we're going to be playing around with here. All right, so this is exercise number 5. A study compared 3 different display panels used by air traffic controllers. Now, each panel was tested for 4 different simulated emergency conditions. So 24 highly trained air traffic controllers were used in the study. 2 controllers were randomly assigned to each display panel emergency condition combination. So again, we have 3 different display panels. We have 4 emergency conditions. So my factor 1 would be my display panel. My factor 2 would be the emergency condition. So I have 3 possibilities for the first, 4 possibilities for the second. That is a total of 12 total treatments that we are going to be looking at. We're going to assign 2 experimental units for each one of those. So we'll need 24 experimental units, or in this case, 24 highly trained air traffic controllers. All right, so the time in seconds required to stabilize the emergency condition was recorded. So when we're using display panel A and we are on emergency condition 1, the 2 experimental units or highly trained air traffic controllers were able to stabilize the emergency condition. One was doing it in 17 seconds, the other in 14 seconds. So obviously in this case, what is different from the last example when we're talking about the gasoline example is the more mileage, so the outcome we wanted to be larger. We wanted more mileage in terms of the gasoline. So a smaller number means we're getting less mileage, a larger number means we're getting more mileage. Now here we're doing the reverse. We're not trying to maximize a number of seconds. Here we're trying to minimize the number of seconds because obviously we want to be able to stabilize an emergency condition as fast as possible. So 17 seconds versus the 14 seconds, well, the 14 seconds is better overall. But again, we're talking about 2 experimental units for each one of the treatments. So this represents my 2 experimental units for each treatment. So for A, that's what I have for the first emergency condition. For the second, I have 25, 24. For 3, 31, 34. And lastly, for 4, I have 14 and 13. Again, I have the same thing for B, same thing for C. Now, if you really wanted to do this, and you're welcome to give this a try, and you'll see how much of a pain this actually is, calculate the sum of squares total, my SSTO, SS1, SS2, and SSInt, and then of course you can calculate SSE by just rearranging. So I'm saying do these by hand just to kind of get an idea of the formulas, to see in general what is actually happening here. You don't do it, it's not the end of the world. All right, so we've already gone through this part here. All right, so when we build our F statistic for each one of these, again, what we need to do is we need to be able to divide out by the correct degrees of freedom. So for SS1, I want MS1, so the mean sum of squares for the first factor. So I take SS1. Now, SS1 has A different levels, so A minus 1 is my degrees of freedom. For my MS2, so my mean sum of squares for factor 2, I have B levels, so B minus 1 is my degrees of freedom. So I take SS2 divided by B minus 1, that gives me my average there. For my interaction, same idea as what we did beforehand when we were talking about the blocking factor. So I look at the interaction. So I have the A levels for factor 1, B levels for factor 2. So I have A minus 1 times B minus 1. That is going to get me my degrees of freedom for the interaction. And last but not least, my error. So my error has a total of A times B different treatments. For each treatment, we assign M experimental units, so M minus 1 times A times B is my degrees of freedom for my SSE. So to create the F statistic, and this is what's going to help us when we do our hypothesis test to determine whether or not we are going to reject the null hypothesis and accept the alternative, or fail to reject the null hypothesis. So my F statistic for my first factor is just MS1 divided by MSE. So the mean sum of squares for factor 1 over the mean sum of squares for the error. Same idea for f2. I take my mean sum of squares for my factor 2, again dividing out by the error. And last but not least, for the interaction. So we see we have 3 F statistics, so we're going to have 3 hypothesis tests here. We'll have a hypothesis test for the first factor, for the second factor. So those are our primary actions or primary primary effects. That's the word I was looking for. The primary effects on the response variable, and then we have the interaction, which is the secondary effect on the response variable. And again, fint is just msint divided by mse. There we go. So my ANOVA table, or as R will produce for us, or a slight variation of this. Again, that first column represents our sources of variation. So I have my factor 1, I have my factor 2, I have my interaction, my error. Again, R is not going to give us this last line, and it's going to give us the additional column of that p-value column. The second column is going to be degrees of freedom. Third column, sum of squares, mean sum of squares for the next one, my F statistic, and my p-values. All right, so before we get into the actual hypothesis test, or the 3 different hypothesis tests that we are going for here, let's actually compute the ANOVA table for exercise 5. Now, I'm not going to do this by hand. We are going to do this inside of R. So let's jump over to my R screen. Here we go. All right, 2-factor emergency condition example. So this starts at line 52. I have a little bit of a blurb here of exactly how we break these things down. So remember when we are creating the ANOVA table, that first input, so we're using the AOV function, that first input is a formula. We have 2 different ways of inputting a formula when we are dealing with an interaction. So one of the things I can do is I can say my response variable, and this is on line 56, my response variable is explained by, so that's my tilde in there, my treatment 1, my treatment 2, and this shouldn't be a star. Let's get rid of this. Delete that. That should be a colon. So treatment 1 colon treatment 2. So this is looking at all combinations of those 2. Now there's a shorter way of being able to do this, and I like shorter ways of being able to do things. So I can say the response is explained by treatment 1 star treatment 2. So what this is going to do, what that star is going to do for us, is it's going to look at the primary effect for treatment 1, it's going to look at the primary effect for treatment 2, and it's going to look for the interaction between the 2. So the formula, which is longer, that first one that's on line 56, or the shorter on line 57, these behave in exactly the same way. So dealer's choice as to which one you want to use. I'm going to stick with the shorter formula, but again, it doesn't matter. They're going to have the exact same outcome in the end. All right, so the first thing that I need to do is to bring in the data. So everything I have on the screen was dealing with the blocking factors, so let's clear things out. So I'm starting with a brand new example. I don't need all of this information that I have up in my global environment. So if I want to clear this out, I can do this in a couple ways, but the easiest way is just at the top right here, you see a broom. So if I just click on the broom, it's going to ask me if I want to remove everything. I say yes, and notice my global environment is now cleared up. So all of the variables that I saved, everything that I did for the first example here that I'm not using anymore, I don't need any of that information. It's a little bit cleaner in here. And same idea with the histogram. I don't need this anymore. So let's go to the broom. Let's clear this up. Yep, we're going to do that. And if I really wanted to clean everything up just a little bit more, I can do a Control L, and that's going to clear up everything in my console as well. So it's kind of like I'm starting from scratch. Now, one thing that I do want to do, I am going to try and graph things in here. So I do need the ggplot package. Now, I did load ggplot in the end of that 3rd lecture or 4th lecture. I can't remember which one it is at this point in time, but if you're paying attention, you know what I'm talking about. I didn't use it for the blocking, but I am going to need to use that now. Now, I did load it. Is it still loaded? That's the question. So what I can do here is I can go up into my bottom right screen, or my bottom right window here, and just under packages, This is going to show me everything that I have installed, so that's currently sitting in my library, and anything that has a check mark has been pulled from my library and I could use in my current session. So notice here that ggplot2 has a check mark. That means it's still loaded, it's still ready to go, so I don't have to load this again. All right, so the first thing that I want to do is I want to bring in the data. So there is an emergency.csv file that is loaded up on Brightspace. So remember to download that. And again, I recommend putting all of the files in the same spot. So under my download section, I have a lesson 2 folder inside of here, or a lesson 1 folder. No, this is lesson 2, sorry. Lesson 2 folder, which contains all of my R files. It contains all of my data files. And remember, when I'm bringing this in, I'm using the read.csv function. So my first input is I'm asking for the file emergency.csv. I'm telling it that that's the file name. Now, if I don't point to the right directory, it's not going to know where to pull this file from. And again, because I've stored everything in exactly the same place, I just need to make sure that I set my working directory correctly. It should still be set correctly, but let's go through this again. So I go to set working directory, to source file location. Again, because I've stored my R files and my data files in exactly the same folder, and this current script file that I have right now for lesson 2 is what is loaded, it's going to say, okay, let's look at where lesson2.r is, and that folder is where I'm going to try and pull everything from. Now, I don't necessarily need to do that. I can go choose a directory. I can do all of these different things, but again, I keep everything in the same spot, makes it nice and easy. All right, so this is loaded. I do get a warning. I'll get a warning every once in a blue moon, not the end of the world. If you get an error, that's a problem. Warnings, not so much of a problem. All right, so I've set my working directory to where it needs to be. So now I'm going to run line 61 of my code here. So just doing a control enter. And notice in the top right corner in my global environment, model input 2, that is the name of the variable. This contains a data frame that has 24 observations in 3 variables. Now, anytime I bring in a file or a table or any of these types of things, it's usually a good idea to take a look at the first couple lines to see, well, what kind of data, how is this kind of set up? Now, I could read out the entire table, and how I would read out the entire table is just calling the variable name. So I can just put in the console, or I could execute on any one of these lines here. I would just type in model input 2. But I don't want all 24 observations. Let's just say I wanted the first couple. Let's say I wanted the first 6. I could use the head function. So there's a head function and a tail function, which will give me the first 6 or the last 6 rows of my data frame. I just want a general idea of what this data frame looks like. Again, I can pull the whole thing, but I just want the first 6 rows. So I'm going to use the head function. The input for the head function is just the name of the variable. So that's my model input 1. Again, control enter. And notice that I have the first 6 rows of that data frame. So I have factor 1, factor 2. So basically, when I'm looking at that very first row, that treatment represents x sub bar 1, 1. So that is going to be when my first factor is level 1, my second factor is level 1. And in this case, since it's the first observation for that, it would be x11, comma 1. And the outcome of that is 17. My second line, I would be x sub 1, 2. And since it's the first observation for that treatment, that would be x sub 1, 2, comma 1, outcome 25. And if we go down a bit, so I have factor 1, factor 2, levels 1 and 1. I have 1 and 1 down here, so this is my second observation, so I have my 17 and my 14. So everything is included here the way I need it to be included here. Now, one thing to note, factor 1 and factor 2. Again, if I go to my top right here in my global environment, notice that factor 1, factor 2, both of these are integers. These are supposed to be categorical variables. So right now they're an integer variable. I need them to be categorical variables. So this is where I use the factor function. So I replace that column inside of my data frame, make it look exactly the same, except this time I'm telling R that this is a categorical variable. This is not an integer variable. So that's just running through that factor function. I'm going to do that for my first 2 columns here. So for my factor 1, factor 2. So just again, control enter for both. And notice in the top right corner now, factor 1 and factor 2, these are factor variables. The first one has 3 levels. Those levels are 1, 2, 3. The second one has 4 levels. That's 1, 2, 3, 4. So it's not going to treat them as numeric anymore. It will treat it as categorical. And it's always good to make sure that, again, you are putting the variables into the correct type. All right, so what do we want to do now? Well, the first thing is let's look at, and the question hasn't asked us at this point in time, but let's look at if there is a possible interaction between factor 1 and factor 2. So this is where I'm going to use ggplot. All right, so how does ggplot work? Well, it works in layers. So the very first layer is basically where are we getting the data from. So when I call my ggplot function, and notice that the bringing it from the library was ggplot2, the function call is just ggplot. So the function called ggplot, my first input, this builds my first layer, and I'm saying the data is coming from my model input 2. It's coming from this data frame. The second layer of this is the aesthetics. It's what I am mapping from that data to the different components of my graph. So for my aesthetics, I'm using the AES function. I'm going to say my X variable, this is coming from factor 1. And notice because this is inside of a function call, I'm not using the arrow notation. I'm not doing an assignment. I'm saying this is equal using the equal sign. So X is equal to my factor 1. My Y variable is going to represent the outcome. So the outcome again is the time it takes to stabilize an emergency condition. So that is a time frame. That is supposed to be an integer, perfectly fine. Now, I want to be able to color and I want to be able to group these things by the second factor. And we'll see exactly why in the picture, but I want to be able to group things by the second factor. So again, my X, this is going to be based upon my factor 1, but I want to be able to group things based upon my factor 2. Now, the next part is adding in the geometry. How do I want my data to look? Now, I could do this as a scatter plot, but my problem is for each one of the treatments, I have 2 outcomes because there's 2 experimental units for each one of those. So what I want to do is I don't want 2 data plots for each one of my treatments. I want a single data plot. I just want the average for that treatment. So what I'm going to do is I'm going to use a very specific function. So this is my stat summary function. So this is already going to do some work for me, and it's going to assign a specific geometry, so how I want my data to look. So the first thing, this stat summary, there's a couple of different functions we can use, but I'm using function mean. So the function mean, and this is where the key part is where I group things, are very, very important. So I'm grouping everything by factor 2. So I'm grouping everything by factor 2. My X values are for my factor 1, but I want to be able to take the mean of each one of these. And again, we'll see exactly what that looks like when the graph comes up here. And what do I want this to look like? What do I want my geometry to look like? I want this to be a line graph. So let's execute this here. And this is the graph that I get. So notice across my x-axis, this represents the different values for factor 1. So factor 1 can take on values 1, 2, and 3. Now for each one of these factors, again, for each one of these levels, for factor 1, factor 2 is going to play a part in it for, again, each one of the possible combinations. So for factor 2, I have 4 levels, 1, 2, 3, 4. So for level 1 of factor 1, this represents here on my x-axis, and I have 4 different spots or 4 different treatments that are associated with level 1 and the 4 different outcomes for factor 2. And again, for each one of these should have 2 possible experimental units, but I don't care about those 2 possible experimental units. I just want the average of the 2. So this is what that dot represents. It represents the average of when my level 1 of factor 1 and my level, in this case my blue, level 3 of factor 2, 2 experimental units. What's the average of that? My average is roughly around 32.5. Okay, so what would we expect to see if there was no interaction? What I would expect to see is that each of these lines are going to be basically parallel. Now, why is that the case? Well, if each of these lines, and they look fairly parallel as is, this would imply that if I transition from factor 1 to factor 2, it doesn't matter which level I'm on, they're all going to behave in exactly the same way. So it doesn't matter which level of factor 2 I'm on, it's all going to behave in the same way. I'm always going to see, when I change from factor 1 to factor 2, I'm always going to see a decrease. Again, regardless of what level of factor 2 I'm on. So the level of factor 2 is independent on there. I'm always going to see that decrease. Or when I'm going from 2 to 3. When I go to 2 to 3 of my factor 1, I always see an increase. So it doesn't matter, again, which level I'm on. I'm always, of factor 2, I'm always going to see an increase. So these all behave in exactly the same way. Now, on the other hand, if something like this one here for my level 1 of factor 2, if this decreased and then continued to decrease versus my level 4 of factor 2 where this decreased and then increased, well, they don't behave the same way. So when I go from level 2 to level 3 of my factor 1, it is important which level of factor 2 I am on because they do behave differently. But in this case, since they are basically parallel, I would highly doubt that there is going to be an interaction. Now, they're not perfectly parallel. If we notice the decrease here, some decrease a lot steeper. For my level 1 of factor 2, this doesn't really decrease all that steeply. When I look at even level 4, this is a sharper decrease here. This is a sharper decrease. This is a sharper decrease. This not so much of a sharp decrease. So maybe there is something different that's happening here, but it might just be a very slight difference. So based upon this, I would kind of be looking at like, well, maybe there's an interaction, maybe there's not. Now, I did have this. This is not part of the question in itself. This is kind of like a side sort of thing. So I have another R file that I've uploaded to Brightspace. Here I have some data that I've created. And let's look. So we're taking kind of a step away from the emergency condition. We'll get back to that in just a second. But I have two different examples here. So let's take a quick look and kind of get an idea of what's happening here. All right, so I'm creating some sample data. I don't need to load my ggplot2 because it's already loaded. So I'm going to bring in this data here. So I'm going to store this in a data frame called data. I know, very original, but just go with it. Let's print the data frame out to the console. All right, so in this case, I have two different variables. I have fertilizer and I have watering. So what type of fertilizer do I use? I use type 1 or type 2. And what level of watering do I do? Do I do a low level or do I do a high level of watering? And then there's going to be something that we're going to measure, so the height of growth of, say, a plant or something along those lines. So we have different heights for these sort of things. So for example here, if I'm looking at fertilizer type 1 under a low level of watering, I'm going to get a height of 30. Fertilizer of type 1 high watering, I'm going to get a height of 50. Fertilizer 2 low 25, high 20. All right. So let's plot these, and I'm going to do kind of exactly the same sort of thing here. I have a little bit different coding. It all kind of works in the same thing. So all different layers that we have on here. So I have, again, my original layer, which is my data frame that I'm using. Then I have the aesthetics, how I'm mapping that data frame to the different parts of my graph and how I want to be able to make the graph look. So the geometry. So that's my line graph here. I'm also going to have some points. Again, let's just take a quick look at this. My points are just my endpoints here just to make sure that things kind of stand out. But again, everything kind of holds true. Okay, so these lines obviously are not parallel. So do we assume that there is some interaction that's happening here? Well, notice that if I go from high level of watering to low level of watering, what do I expect to see on the growth? Well, if I'm using fertilizer of type 2, I have growth of size 20, and I'm going up to growth size of 25. So if I'm reducing the amount of watering frequency that I'm doing, using type 2 fertilizer, I'm seeing a growth. Now, on the other hand, if I'm looking at fertilizer type 1, if I'm doing a high level, I have 50. If I'm doing a low level, I'm down to 30. So this is actually reducing it down. So do these things behave together? Or is there some sort of interaction that's happening here? Well, it definitely would appear that they do not behave in exactly the same way. My lines are not parallel, so I would be expecting that there's some sort of interaction that is happening here. Okay, so let's look at the similar sort of an idea. So again, another data plot. This time, again, we're talking about the amount of light and the fertilizer type that we have. So a lower high light, and again, growth. So if I graph this one, again, going from fertilizer type of a high, I guess, grade of, we'll call it that, a high grade fertilizer to a low grade fertilizer. What happens for both? So the different colors here represents the amount of light that they would get. So obviously a high amount of light is better overall. But if we're looking at these two things, they behave again in exactly the same way. So is there really an interaction between the two? And in this case, I would probably guess that there's not really an interaction. These lines are not perfectly parallel, and I have very little in the way of data points to go with. But again, notice that they behave in the same way. So if I'm going from high to low quality fertilizer, or this fertilizer amount, so a high amount to a low amount, and the amount of light, well, they both decrease in terms of growth. So because they're behaving in relatively the same way, it is independent on the amount of light. Now, there obviously is going to be a better choice. So when we look at the primary effect from factor 1, we look for the primary effect of factor 2, there's going to be times where things are going to be optimal, and we're going to be able to determine which one of those are. Is there an interaction? Do they depend on one another? In this case, no, they don't. All right, so let's jump back now to the example that we were playing around with. So lesson 2, let's go back to lesson 2 here. And I'm going to go back to my slides. Okay, so we've built, no, we haven't built the ANOVA table. Let's go back to R, there we go. See, this is always why it's so much better to be doing this in person, because someone would be like, hey, wait a second, you haven't built the ANOVA table. We need to go back. And if I didn't catch that, I would continue on. We wouldn't have built the table, and it would probably be about 20 minutes into this going like, oh crap, I messed up. I'm not going to edit this. Just deal with it, sorry. All right. So let's build the ANOVA table. So this is starting on line 73. I'm going to store the information in model 2. That's going to be my variable name. Again, I'm using the AOV function. And my first part is my formula, and I'm going to use the shorthand for this. So I have factor 1, factor 2. Those are the names of my first two columns. So I'm saying the outcome, which is also the name of my column, that is my response variable. So my outcome is explained by factor 1 times factor 2. So that's going to give me the primary effect for factor 1. It's going to give me the primary effect for factor 2, and it's going to give me the interaction. My data, this is coming from my model input 1. That is my data frame. So if I run this and then I run the summary, again, my degrees of freedom, 2, 3, and 6. So 2 for factor 1 because I have 3 different levels. So 3 minus 1 gives me my 2. For factor 2, that is my emergency condition. There's 4 of them. So 4 minus 1 gives me my 3. 2 times 3 gives me my 6. And voila, I've got just about everything. I have the sum of squares calculated for each one, the mean sum of squares, my F values, and my P values. Now notice in terms of my F values, for my factor 126, and do recall that when the F value is close to 0 or 1, that's usually indicating that we're going to be failing to reject that null hypothesis. When it's much greater than that, we don't know because we don't have that critical value, but when it is greater than that, we have the opportunity to reject the null hypothesis, there we go, and accept the alternative. So 26, that could be fairly big. 100, that's definitely big. For my interaction, my factor 1 colon factor 2, 0.663, very close to 1. chances are I'm going to fail to reject the null hypothesis on that one and say that there is no interaction, which we kind of already got based upon the graph. All of the lines were fairly parallel. So from a rough guess, I would say we're going to reject the null hypothesis for factor 1 and say one of them is better. Again, factor 2, one of them is better for the interaction, doesn't really matter. Okay. Now let's go back to the slides. Okay, so at this point, all we're going to be talking about is the 3 different hypothesis tests. I'll let you read through them yourself because basically these are the same as absolutely everything. The null, the alternative, again, there is no difference between the effects of the levels of factor 1 versus at least one of the levels are different. I have my F statistic, I have my critical value, so each one of the critical values will be different because they are coming from a different F distribution based upon the degrees of freedom. So if I'm looking at my F statistic, what is my degrees of freedom for my MS1? What is the degrees of freedom for my MSE? My denominator is always going to be the same. My numerator is going to change. And then whether or not I I reject or fail to reject the null hypothesis, I can do this using either the critical value or I can do this using the p-value. So no difference there. Again, that's the same for factor 2. So the only real change, again, that null hypothesis, no difference exists between the effects of levels of factor 2. And last but not least, to test the difference in interaction, my null hypothesis is no interaction exists between factor 1 and factor 2. And of course, the alternative is an interaction does exist. Now, highlight this part here. Again, if we reject the null hypothesis, it states that there is a difference. It's not telling us what the difference is. It's not saying this specific level here, this specific level here. We need to run a pairwise comparison afterwards. But at least we know there is a difference. If we fail to reject that null hypothesis, so we're making the claim that we don't have enough information to say that there is a difference, well, I don't need to do a pairwise comparison afterwards because there is no difference. I have no information past that point in time. But if there is a difference, I need to run that Tukey HSD function to be able to tell, well, where is that difference? Where does it lie? All right, so for exercise 7, let's go through this. We're going to use an alpha, so a level of significance being 0.05, so 95% confidence or a 5% risk of a type 1 error. So that is rejecting the null hypothesis when the null hypothesis is in fact true. All right, so we want to test for interaction. We want to test for the significance of the display panel effect. So that's my factor 1, and for the significance of the emergency condition, that's my factor 2. And again, a rough guess based upon all of these things is that I am going to reject for the display panel, I'm going to reject for the emergency condition. So there is going to be a difference between those two. I'm going to fail to reject for the interaction based upon the F statistics that we've calculated, or that R is calculated for us, but we've interpreted very, very quickly from the table. Okay, so let's go back here to R, make that screen a little bit bigger for us. You can still see up on top where I am dealing with the PowerPoint here. So let's look at, for part A, what is our critical value? And I need to grab this from R. Okay, so if I am looking, and again, the first one that we are dealing with here is our interaction. So my degrees of freedom for my interaction is 6. My error, degrees of freedom, is 12. So when I use that QF function again, my first input is what is the level of significance. That's my 0.05, my 6 and 12 of my degrees of freedom. And remember, from this distribution, I want that right tail. I want the last 5%. So what F value is the starting point for that last 5% of this distribution? And the idea of this distribution is that the null hypothesis is true. So this is where we would expect to see the ranges of F values if this was true. But where's that cutoff point? So for us, that cutoff point, or that critical value, oops, I don't know what I did here. Where is my mouse? There's my mouse. So running line 77 gives me a cutoff point. Oh, I know what I did here. I switched over this screen. I don't want to switch over this screen. I wanted my other screen back. Go back. There we go. Excellent. All right, so my critical value... No, go back. Don't do that. My critical value in this case is 2.99612. So again, if I have my distribution, and hopefully you can see it right up top, right over there, perfect. That last 5%, my most extreme values start at 2.99612. So any F value to the right of this, I would reject my null hypothesis. Anything to the left of this, I would fail to reject. And in this case, my F value, or my F statistic that was calculated here, is 0.663. So that lies in the fail to reject range. Okay. So we don't have enough information that say that there is, in fact, an interaction. So we fail to reject. For B, now I'm looking at factor 1. So again, going back over to my ANOVA table, which is right over here, my degrees of freedom are 2. My error is still 12. So if I run this line of code on 78, again, my QF, where is my thing? There we go. QF 0.05, my level of significance, 2 and 12 are my degrees of freedoms, and I want the lower tail. And I'll run the line right after because that'll give my critical value for C as well. All right, so for B, my critical value is equal to 3.88, 5,294. And for C, my critical value in this case is 3.49, 295. 295. There we go. So that is the starting point. So any F values to the right of that would fall into my rejection range. Anything to the left of that would fall into my fail to reject range. So my F value for B, based upon what I have here, is my 26.495. And my F value for C, this is for my factor 2, is 100.805. So in both cases, they are to the right of the critical value, so we reject H naught except HA at alpha 0.05. Obviously, I'd write this out a little bit more exactly what each one of these means, but again, that's the general idea. So for each one of these, again, for part B and part C, when we're looking at the primary effects for factor 1 and factor 2, we're rejecting the null hypothesis, which states that there is no difference between the different levels. In this case, we're saying there is a difference between the two levels. So it does matter which display panel we're using, and it does matter which emergency condition that we are on. Now, the combination of the two, are dependent on one another? They are not, because again, that interaction is false. All right, let's look now. I always do this. Where is my mouse? There's my mouse, or my cursor for my mouse. There we go. Back to my slides. Clicky here, movie here. There we go. So now that we've established that there is a difference in my factor 1 levels, there is a difference in my factor 2 levels, I do have to run the Tukey simultaneous confidence intervals. So again, this is using the studentized range distribution, which is a distribution that allows us to not drop the type 1 error, because we want to keep that consistent through each one of the pairwise comparisons that we are dealing with. So for each pairwise comparison, we want to be 95% confident that the true difference lies somewhere in the given range. And when we look at all of them at exactly the same time, we still want that 95% confidence. So these are just, again, my formulas for each one of these. Again, no big deal there. Again, if you want to go through the formulas, you're more than welcome to for that. Again, not the end of the world. We've already kind of seen that, or we've seen that for the one-way ANOVA. We've seen it for the two-way. There's no real difference when it comes to the, we've seen it for the one-way. We've seen it for the blocking. There's really no difference when it comes to the two-way. And again, R is going to do all the calculations for us. All right, so at alpha being 0.05, so 95% confidence, we want to do a pairwise comparison on the display panel. So that is for my factor 1, F1, and for my emergency condition, that's my factor 2. Well, let's do that first, and then we can answer the next part afterwards. So going back to R, again, I want the confidence intervals for my factor 1, so I'm doing two inputs here. My first is what my model for my ANOVA table was saved in, so that's model 2. And I want the pairwise comparison just for my factor 1, and I want it for just for factor 2. There we go. Right, so I have 3 different pairwise comparisons for my factor 1. So again, this is my display panel. So my first line here tells me if I replace display panel 1 with display panel 2, I'm going to have a difference of negative 3.250. Okay, so the time it takes to respond to emergency conditions decreases by 3.25 seconds. So this would be telling me if I replace 1 with 2, 2 is going to do better at being able to stabilize faster. Now, if I look at my lower and upper bound, both of these are negative, so they don't cross 0, so it is significant. I am 95% confident that the true difference in the population parameter for replacing display panel 1 with display panel 2 is always going to be negative. Okay, so this tells me that 2, no, go back, there we go. 2 is better than 1. Okay. If I replace 1 with 3, ooh, now I see an increase. So that tells me that if I replace display panel 1 with display panel 3, it takes me longer at this point in time to be able to stabilize an emergency condition. I look at my lower and upper bound, both are positive, so it does not pass over 0, which means I'm 95% confident that the true population parameter is always going to be positive. Therefore, 1 is better than 3. All right, so 2 is better than 1, 1 is better than 3. What's the difference between 2 and 3? Well, obviously, this is going to be straightforward in this case. So if I replace 2 with 3, that's my very last line, I'm going to see an increase of 7.35 seconds. 7.375 seconds. Both my lower bound and upper bound are positive, which means I'm 95% confident that the true population parameter is always going to be positive as well. So replacing 2 with 3 is always going to be worse. So 2 is better than 3. So 2 is better than 1, 2 is better than 3, 1 is better than 3. So 2, 1, 3 is my order of my display panel. So we see that right up top, right there. Perfect. So that's part A. Part B. Okay, so we have a little bit more in part B, and only a little bit more in part B because I have 4 different levels. So 4 choose 2 is going to give me 6 possible combinations. Now, some of these I will be able to tell. Maybe some of them I won't be able to tell. But let's look through these. So if I replace emergency condition 1 with emergency condition 2, I'm seeing an increase. So it takes longer. We can stabilize 1 faster than we can stabilize 2. And our lower and upper bound are always going to be positive. So that tells me that 1 is better than 3. Sorry, 1 is better than 2. If I replace 1 with 3, again, I see an increase. My lower and upper bound are both positive, so that tells me that 1 is better than 3. And if I were to do 1 and 4, I see a decrease. Both my lower and upper bound are negative, so I'm 95% confident that the true difference between replacing the emergency condition 1 with emergency condition 4 is always going to be a reduction in time, so 4 is better than 1. Okay, so that's my first 3. My last 3, if I replace 2 with 3, I see an increase. Again, lower and upper bound are both positive. So 2 is better than 3. Replace 2 with 4, I see a decrease. Lower and upper bound are both negative. So again, 95% confident it's always going to be negative. So 2 is better than 4. And lastly, 3 with 4, I see a decrease. Lower and upper bound, both negative, so 3 is better than 4. All right, so 1 is better than 2, 1 is better than 3. So 1, 2, 3. 4 is better than 1. 2 is better than 3. Okay, that's how I already have it lined up here. One second here. So, did I do this calculation? 1 is better than 2. 1 is better than 3. 4 is better than 1. 2 is better than 3. I have not had enough energy drinks right now. Why am I missing something here? Why do I think I'm missing something here? Mm-hmm. Mm-hmm. See, this would be great that I would have someone in the room to be able to point this out. What I made my mistake on here. I'll give this another second before I quickly move on. Um, all right. Can't think off the top of my head. I'll probably, as soon as I stop this video, it'll be like, oh yeah, this is exactly what I meant. Um, See, the worst part is I do not go back and edit these things. Okay, so ah, it's my last lines here. Ah, there we go. See, it's a good thing I didn't stop this. Blah, 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 blah. Okay, so second last line. If I replace 4 with 2, I see a decrease. So 4 is better than 2. And last but not least, if I replace 3 with 4, 4 does better. So 4 is better than 3. Okay, jeez. Who let this guy teach this course? What's going on? This is why I shouldn't be doing things online. I should be doing this in person. But they really wanted this to be done online to give people the flexibility to watch these from wherever to so on and so forth. I'm sure it'll work out in the end, but you just kind of have to put up with that. And realistically, if we were doing this in class, you just see me staring at the board going like, I don't know where I went wrong. But we figured it out, or I figured it out. It was all the positive thoughts people were sending while watching this video that I was able to do that. That's what it is. Yes. All right, so I have 1 is better than 2, 1 is better than 3, 4 is better than 1, 2 is better than 3, we already have by default. 4 is better than 2, 4 is better than 3, so this is the lineup. So it's 4 to 1 to 2 to 3. Okay, there we go. Now, if I go back and actually look at the graph, where's my blah, 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 here we go. We can see exactly this. So remember, the different colors here are lining up as to which one's going to be better. Overall, they all behave in the same way, so it doesn't really matter in terms of the interaction-wise. But I want to be able to minimize the amount of time, so we just kind of read these in order. So what's the bottom one? This is 4, then I have my 1, then I have my 2, then I have my 3, which is exactly the order that I have up here, 4, 1, 2, 3. And when I am looking at, if I go from 1 to 2, 2 to 3, well, which ones are better overall? So 1, my best here is when I'm on this one here. 2, I'm all the way down here, so I'm minimizing faster, so 2 is better than 1. And 2 is better than 3, but also 1 is better than 3. So and again, they all behave in exactly the same way. So the order would be 2, 1, 3. Which is exactly what I have right there. So based upon the picture, we would have been able to tell all this. But the idea is the picture doesn't tell us absolutely everything, because was this just done, and that's the question that we primarily ask, was this just done based upon the sample that we have taken? Was the sample large enough? Was there enough significance to that? So was it just random sampling error, or is there statistically something significant about this? And this is where we need to run that hypothesis test. We need to see what is our critical value, what is our rejection region based upon our level of significance. All these things need to be taken into play, or taken into account when we are doing that. So that puts us at just over an hour's time. So that's good for another lesson. Again, these would all be. I do try to get these around the hour and change mark. I do find that if I was doing it in class, I would get a lot more questions. Now I'm getting those by email, so I'm taking that extra time to respond to emails. But when there's no one to stop me for questions, it goes a lot quicker. So I'm also trying not to make these like an hour and a half long because no one really wants to watch it for an hour and a half. We get the information in there. You have the chance to go back and watch it, and you have a chance to answer the questions. All right, so that's everything for module number 1. We'll begin module number 2 in the next lesson. So up to this point in time, this is everything that you need for assignment number 1. Again, TAs are around to help you if you have any questions. I'm going to do another video on how to do the markup. So that's how we are going to present the information. So that'll come probably in the next day or so. Or it might already be posted by the time you end up watching it. So that's it. That's all for today. We'll see you back here next time. And that's it. That's all. See ya. Now where's my mouse? Why do I keep losing my mouse? There's my mouse. Later.